Hi everyone, welcome to this virtual ASPLOS 2020 presentation coming to you from Annapolis, Maryland. I'm Christian DeLozier and I'm at the United States Naval Academy. This is work done with my collaborators at the University of Pennsylvania and Intel Corporation, Kavya, Lakshminarayanan, Gilles Pokam, and Joe Devietti. And this is our work entitled Hurdle, Securing Jump Instructions Against Code Reuse Attacks. So first off, what problem are we trying to solve? So in a standard execution of some application, we might expect that condition 1 is true, condition 2 is true. We set this function pointer to go to function 1, and then we call function 1 through that function pointer. That might be what we expect the application to do in a normal execution scenario. What an attacker might have the application do in a code reuse attack is to instead skip around that if statement, skip around the control flow that we expected to see, and then call some other function like exec in order to execute some other program to gain escalated privileges or what have you. And this could be exec, mprotect, any other sort of function that gives the attacker more power. So we want to ensure with Hurdle that applications follow the control flow that we expect them to follow and don't end up following some divergent control flow that we would only expect to see in a code reuse attack. So how do we do this? Well, we start off with an uninstrumented executable, and we run that executable, we run that application with a set of training inputs that are representative of the control flow that the application should follow. And while running the application, we record a set of control flow histories. Essentially, at every indirect jumper call, we record the previous n events that have led up to that control flow. In our case, we use 8 events. We record basically what the control flow has done up until that indirect call or jump. We then pass those control flow histories and some additional security properties as constraints to an SMT solver, which in turn produces a set of patterns that we can check at runtime. We insert those patterns into the executable using binary instrumentation, and we end up with a Hurdle executable that has been secured against code reuse attacks using what we call gate patterns to ensure that the control flow of the application matches the expected control flow based on the histories that we recorded. So for the rest of the talk, I'll give some background on control flow integrity that we build on to create Hurdle, and then I'll discuss the threat model that we used in designing Hurdle. I'll talk about fantastic gate patterns and how to find them and how we use those in Hurdle, and then I'll discuss the architectural support, since this is of course ASPLOS, that we use to make Hurdle efficient. And finally, I'll discuss the security, usability, and performance of the Hurdle system. So to get started, attackers used to be able to attack system using a simple attack based on shellcode and exploiting some sort of memory safety vulnerability. So the attacker could write some shellcode that does whatever they want to do, translate that into assembly code, and then translate that assembly code into machine code, and just simply exploit a memory safety vulnerability to insert that machine code into the running application, and then redirect the control flow or divert the control flow to run their shellcode. This is pretty easy to prevent though, using write XOR execute protections to ensure that the code that is written into the system can't be executed, and if you overwrite something in the code segment, or you can't overwrite things in the code segment. This prevents the simple type of attack, but attackers are clever, and they've been able to get around this protection by using gadgets. So gadgets divide the original shellcode assembly into multiple chunks of assembly code that we might find in a regular application. So each of those gadgets does some smaller amount of work than the original shellcode, and then redirects again to call the next gadget in the chain. And attackers can pretty readily find these gadgets within existing code, especially if there are libraries like libc that are included with the application that have pretty well-defined pieces of code that can be used to interoperate, basically reproduce that shell code that existed originally. So what are some mitigations for code reuse attacks? The first one that we need to know about is the shadow stack. So the shadow stack ensures that calls return to the correct address, or ensures that calls return from a function call to the correct address that they should have returned to in the first place. So if an attacker smashes the stack, overwrites a return address, this will either catch it or prevent it from being overwritten and be able to return to the correct address in the code. This prevents return-oriented programming attacks, return-oriented code reuse attacks, but it doesn't prevent anything using jumps or calls. So to help with jumps or calls, we can use landing pad instructions. These ensure that calls and jumps land at one of some number of predefined addresses in the code, things like the entry to a function or the case statement in a switch statement. This partially prevents call and jump oriented programming attacks, but there are still some opportunities for the attacker to use these gadgets that start with a landing pad instruction and end with another indirect jump or call. Intel CET provides both a hardware shadow stack and landing pad instructions in the form of an end branch instruction. This is coming soon, control enforcement technology, and should help to prevent code reuse attacks, but still doesn't get rid of all of them. And finally, there have been a number of approaches to control flow integrity that try to ensure that the control flow of the application follows what is expected. Our approach builds on context-sensitive control flow integrity techniques. So finally, let's look at Hurdle's threat model. So we require some of these existing protection mechanisms. Namely, we require that we have write XOR execute protection to ensure that the attacker can't simply insert and run new code on the system to get around our protection. And we also require that Intel CET has been enabled on the system. So we assume that we have this hardware shadow stack, and we assume that we have end branch instructions that indirect jumps and calls must target. So then our system has to target end branch gadgets. We have to ensure that anything that begins with an end branch and ends with an indirect jump or call can't be used in a gadget chain. We also make some assumptions about the attacker. So we assume the attacker can arbitrarily modify memory by exploiting memory safety vulnerabilities. We also assume that the attacker has to execute at least 2 gadgets in a chain in order to perform a code reuse attack. So if they only execute a single piece of code, a single gadget, we would consider that a data-centric attack, and we don't prevent that type of attack. We also don't prevent anything involving JIT compilation or handle JIT compilation or dynamically linked libraries because these are a bit too complicated for our system at the time for our prototype. We leave these to future work. So next, let's look at what gate patterns are and how Hurdle uses them to secure applications. So again, going back to our example from the beginning, we may have some expected control flow for an application. We may have some unexpected control flow. So Hurdle uses what we call gate patterns to make sure that when we make an indirect branch or call, the control flow history up to that point matches the pattern that we expect. So here we might expect that these if statements here can execute, but that if we jump around this first if statement, we can't execute this indirect branch. And that's what the pattern encodes, is what the expected control flow is at an indirect branch or jump. So we first record these control flow histories based on some training inputs, and we do this using a Hurdle alphabet that is a bit more complicated than your standard branch history register alphabet. So usually we just have taken and not taken branches. For Hurdle, we need to be a little more specific about the control flow that's happening. So we record not taken and taken conditional branches, unconditional or taken branches, and direct calls. These are all direct branches, and then we have our indirect branches, which are returns, indirect jumps, and indirect calls. I've labeled the control flow graph on the right here to show that we come into this function with an indirect call. We then have some not taken branches for the if parts of the if-else statements, taken branch for the else part of the if-else statements, unconditional branches to get to the code after the if-else statement, and then finally some indirect calls to leave via the function pointer. So we label the edges of this control flow graph, and then we can record the histories based on what we've seen prior to these indirect jumps and calls. So again, using this label control flow graph, we can follow the path that we took to get to an indirect call. In this case, fptr is our call to a function pointer. And if we track backwards from that indirect jump or call, we can record the history that happened right before that indirect jump or call. So here, we're just following backwards along the green paths that we have a U, an N, and an N. So that's our first indirect call history. We might also see the other side of this during the execution where we have U, T, N. We're only recording 3 events here because even though our system uses 8, it's a bit too complicated to show 8 control flow events for the presentation. But we would record 8 of these events. We then condense these histories into a single pattern. So we essentially just take the union of each column here and produce that final gate pattern. So we expect that this gate pattern will match any feasible control flow through the control flow graph that we saw during one of these training input executions. And this is the first set of constraints that we pass into the SMT solver for it to solve for this gate pattern. The second set of constraints are what we use to prevent gadget chaining. So we want to ensure that if we have one indirect branch A and another indirect branch B, that we can't chain from branch A to B unless that chain is required by the application's control flow. So if we do have one indirect branch that calls another indirect branch, we want to make sure that that can happen at runtime. But if we don't have that requirement from the application, we want to ensure that there is no gadget chaining from A to B. So how do we do this? Well, we start off with A's gate pattern. So we're assuming that the attacker can manipulate the control flow, execute some sort of memory, exploit some memory safety vulnerability and change the things in memory, but they can exploit the control flow well enough to follow whatever control flow they want up until A, and ensure that gate pattern at A passes. So we're starting with A's gate pattern. We're assuming that this passed the check. We then know that A is going to make an indirect call because that's what happens at A. A is an indirect call. So we shift the pattern over to the right that we passed at A, and we add in the indirect call that occurs at A. We then check this against B's gate pattern using the intersection operation, and we want to check whether gate pattern is empty for some column. So we want to ensure that if we're not supposed to branch from A to B, that we want to have some empty intersection, which means that the check at runtime will fail. If we followed the pattern up to A correctly and then branch to B, we should have a failure in this check. So we can see that C and C match. This does correctly match the pattern, so we wouldn't have a failure there. But U and N don't match. There's no way for the attacker to choose the control flow history. Given that they can only execute an unconditional direct branch, they can't make that match a not taken direct branch. And then finally, we can see here that the final element would actually match because the attacker could choose the T, the taken branch, in this pattern, and that would match B's pattern. So we give some power to the attacker. We assume that they are smart enough to basically choose whatever pattern they want, whatever history they want up until the first branch. And then we make sure that this doesn't match for the second branch to make sure that there's no chaining from A to B. There are cases where, of course, all of these match. There's no empty intersection, and we discuss how we handle that in the paper using synthetic branches, but it's a little too in-depth to cover in a 20-minute presentation, so please see the paper for more details. So that's how gate patterns work and how we find them. Let's look at the small amount of architectural support we need to make Hurdle efficient. So we add two things to the architecture. The first is the hcheck instruction, which encodes the gate pattern to be checked before each indirect jump or call. This encodes the exact pattern that we need and then the opcode for the hcheck. And this operation occurs at decode. So we want to ensure that if there is a speculative path, like in the Spectre attack, that the attacker wants to execute that is not part of the standard control flow of the application, we do want to prevent that control flow. So we want to keep from executing speculatively things that we don't need to execute anyways. We do check again at commit time to make sure that whatever predicted branch state we used at decode was actually the branch state that we took, and make sure that this check does pass at commit time as well. We also add an extended branch history register to the architecture. So this is a 7-bit, one-hot encoding of the Hurdle control flow alphabet. There are 7 different letters in the Hurdle control flow alphabet. And we add this in addition to the existing branch history register to not overly complicate the branch prediction logic in the architecture. We size this at 8 entries for a total of 8 entries times 7 bits for 56 bits. And we found that this was enough history to be able to differentiate between indirect branches in the applications that we tested, but not so large that the instruction encoding became unwieldy or that the SMT solver runtimes became too long. So finally, let's look at the results on security, usability, and performance with Hurdle. So in terms of security, what Hurdle does is further restricts the number of control flow paths that the application can take compared to if we were checking against the static control flow graph of the application. So we can check against the static control flow graph, make sure that the application is following what we would expect statically, but Hurdle is a bit more specific because it does rely on some dynamic informations. So for this study, we measured the number of control flow paths that were possible if we checked either the static control flow graph, used hurdle gate patterns, or looked at the actual dynamic paths that an application took. Here we show the applications with the smallest number of static control flow paths, the median number for matrix, and then the largest number for typeset. These are all from the MI Bench suite. We can see here that hurdle really limits the number of static control flow paths that are allowed. So we reduce the number of paths that we would validate as being reasonable by using some of the dynamic information to limit what the application is allowed to do. We're still not quite at the dynamic paths allowed, but if we look at a larger application like typeset, hurdle gets pretty close to approximating the dynamic paths while still being able to compress to this gate pattern and not use up more memory in both the executable and possibly in actual system memory as well. We measured the usability of hurdle by training it on smaller inputs and testing on larger inputs for each benchmark. We found that our SMT solver could find the gate patterns sometimes in as little as 1 second at a minimum, and then for the largest applications we looked at in up to 27 minutes. We do realize that with even larger applications, this could become an issue that the SMT solver might not be able to find a satisfiable assignment or find something that is unsat in a reasonable amount of time. We leave this to future work to work around this issue. We found that hurdle exhibited false positives on 9 of the 44 benchmarks due to the fact that we were training on a smaller input and testing on a larger input and sometimes a more complicated input. This was due to the fact that the smaller inputs may not exhibit the same control flow as the larger input, either because they don't follow certain paths through the control flow graph, or that we don't even see in some cases the indirect branches or calls that were used in the larger inputs. However, we found that all of these false positives could be solved with a technique called static pattern stitching that we have more details on in the paper. But the gist of the idea is that we reconstruct the state using the Intel CET shadow stack and the extended branch history register to figure out if the pattern that we've seen recently matches some static pattern. So we have to fall back to static checking here, or static control flow graph checking, which isn't great for security, but is better for usability because we don't have a false positive that might be a problem for the user. We also performed an in-depth study on image magic. So in this case, we used 50 different image inputs on a set of filters that image magic provides. And we were able to cross-validate that using a subset of those 50 images, we could train hurdle to recognize a different image as the test input. So to train hurdle to have the correct control flow patterns to ensure that we didn't run into false positives. And at a maximum, we needed 18 of the subset, an 18 image subset of that full 50 images. But we were able to train it in any of the cases. So we found that in general, if you have a reasonable set of test cases for your application, hurdle can figure out the control flow that your application should take during its execution without running into false positives. And in general, we often find that these bugs crop up in sort of untested places in applications that you maybe don't want users to be running, and even still, you may not want an attacker to be able to exploit. So finally, let's look at the performance of hurdle. We found that overall, hurdle had a runtime performance overhead of 1%. We did see larger overheads on some benchmarks like string search because it had a very short runtime, and that magnified the loader overhead. So everything that happens before your actual application starts to run involves a lot of indirect control flow. And on a short application like string search, that overhead gets really magnified by the short runtime. We also saw high overheads in benchmarks like Omnet PP that had large amounts of indirect control flow due to the use of virtual functions and function pointers. But again, overall, the runtime was fairly low at 1% overhead and seems reasonable for use in production. So thanks for tuning in. If you have any questions about the talk, I'll be happy to answer them on Slack or via email at delozier@usna.edu. Thanks again, and I hope you enjoyed the talk.